Hello, for our AP Physics final project, we built a flywheel launcher for the VEX Robotics competition game, Nothing But Net. My name is Josh Geiser.
And I'm Elliot Berman. The objective of Nothing But Net is to score those balls into either goal on the opposite side of the field. Robots must fit within an 18-inch cube during the entire match, with some exceptions depending on the location of the robot and time in a match. Scoring inside the goal is the biggest point generator, and so is the biggest focus. The top goal is essentially a pyramid with a face missing. The bottom of the pyramid is 36.16 inches above the ground, and the top of the pyramid is 45.24 inches above the ground, making the pyramid 9.09 inches tall. The pyramid is 21.91 inches wide.
The Nothing But Net balls were not available when we did our testing, so we used the previous game's balls instead. Clean Sweeps balls have very similar characteristics. Both have a diameter of 10 centimeters and are made of polyurethane. Clean Sweeps balls are slightly heavier and have a different coating protecting the internal foam.
Because there are up to 104 balls in play during a match, and because robots may only manipulate up to 4 balls at a time, being able to score balls anywhere on the field is a must. The flywheel is an ideal solution to this problem, as the angle and speed of the wheels can be manipulated to create different trajectories.
We want to work towards the most extreme case, where the robot fires from the opposite side of the field. This means the trajectory must intercept at a distance 3.81 meters away and 1 meter high.
We went through a couple configurations before being satisfied with this final design. Initially, we did not use any external gearing and used the turbo internal motor gear configuration. We found that the wheels slowed down when the balls passed through. We had two options: either decrease the speed of the wheels to gain more torque and the motors would be able to overcome the extra forces required to launch the ball, or we could increase the speed in order to increase the angular momentum and make it more difficult for the wheels to slow down due to that extra inertia.
Slowing down the wheels to the high-speed internal motor configuration did not fix our issues, so we moved to external gearing and went back to the turbo gear configuration. The external gearing configuration gave us a lot more momentum, and the wheels do not noticeably slow down when a ball passes through.
We spaced the wheels out so that there was a 7.62 centimeter gap between the two wheels. Due to the limitations of the metal, we can only increment the spacing by ½ inches. We want the wheels to be as narrow as possible in order to minimize the amount of slipping between the wheels and the ball. The gap determines the normal force. We found that any narrower would squeeze the ball too much and stall the motors. The diameter of the wheels is 5 inches and each wheel weighs 160 grams. Our external gear configuration was a simple gear reduction. The motor powered an 84-tooth gear that spun a 12-tooth gear containing the wheels. This creates a gear ratio of 7 to 1. This means that for every rotation the 84-tooth gear completes, the wheel will complete 7 rotations. This also translates into the wheel having an angular velocity 7 times greater than the 84-tooth gear. The turbo gear configuration creates an output of 240 RPM and a stall torque of 0.7 Newton meters. Doing the math, the angular velocity of the wheels is 1,680 rotations per minute. The linear velocity at the edge of the wheels, therefore, is 24.5 meters per second.
This slow motion capture of the ball being launched shows that the wheels barely slow down when being launched. This video was captured at 1200 frames per second. In the top video, we analyzed the launch speed of the flywheel by using video analysis software to track the ball as it exited the flywheel. Using Tracker, we determined that the launch velocity is approximately 11.1 meters per second. The bottom video once again demonstrates that the wheels do not noticeably slow down when the ball is fed through. This time from the top. We experimented with several angles to determine a relationship between launch angle and distance traveled. In this video, we angled the launcher at 35 degrees and measured the distance using Tracker.
After many trials and several angles, this data was plotted. A power series regression fit the data the best and is approximately a square root function, as you can see by 0.4939. We
pulled the data from the 15-degree launches and worked backwards to determine the initial launch velocity of the ball. To simplify the calculation, we disregarded the fact that the ball was launched from a height of approximately 16 centimeters. Having a launch height greater than 0 would decrease the launch velocity compared to a launch without an initial height.
Using this calculation, we found that there's approximately a 9% error. This plot shows our data and the power regression line in red. We calculated the velocity for each data point and found the average to be 9.53 meters per second. We plotted range as a function of angle using the projectile motion equation. Another thing we had to account for was the true launch height. As the flywheel was tipped back, the launch height decreased. The y initial equation accounts for this error. The dotted lines represent one standard deviation above and below our computed mean velocity.
Using our power regression equation, we calculated the predicted distance the ball would travel at a launch angle of 42 degrees. We placed the box at the predicted distance of 7.9 meters from the launch point and launched 3 balls, all of which landed inside of the box. This illustrated the accuracy of our regression line. There were several sources of error inherent in our experiment. We discovered that some balls had different firmness. This would affect the ability of the launcher to grip the balls, and we noticed that despite holding the launcher at the same angle, some balls would travel shorter distances. After running the launcher non-stop for several minutes, the motors overheated and the wheel stopped spinning. The time it took for the motors to overheat was outside the duration of a match, so we're not concerned this will be an issue.
Another systematic source of error we discovered was where we placed the balls relative to the wheels. If we placed the balls lower relative to the wheels, the balls would be fired down because the balls would travel through the path of least resistance. When the ball was placed higher, the wheels would grip the lower part of the ball and give it lift and therefore a higher trajectory. To alleviate this during our data collection, we consistently put the balls high. Our final source of error is air resistance. Due to the lightweight and low speeds of the projectiles, air resistance was not a major factor, but did noticeably increase as the angle increased. This is evident because as the angle increased, the actual distance traveled was lower than the predicted value by the range equation.
This project demonstrates the components that are necessary for a robot competing in the nothing but net competition. Varying the angle of launch allowed us to determine different distances that the balls could be launched, depending on the distance the robot is from the target.
Overall, we found that there is a strong correlation between the angle of launch and distance traveled of the ball. We were slightly concerned that the correlation would be weaker due to the effects of air resistance, but it was not.
And here's that 6.